So I promised that I would remove the VFO from the low-frequency mobile receiver that we took out for a ride last week. Basically, this VFO is nothing special. It's a couple of FETs and a transistor with a little bit of filtering in the output. So it's such a standard circuit that I want to show you a typical VFO done by W1FB. And it's very representative of what I've done here. It's a simple Colpitts oscillator. So let's take a look what's inside this VFO. So there are so many articles and so much advice on building VFOs, stable VFOs, that I'm just not going to reinvent the wheel. I'm going to use what's regarded as one of the best sources for advice on analog VFOs. Some of these early solid-state VFOs using FETs. And this reference is by Frank W. Harris, Kilo Zero India Yankee Echo, who lives in Colorado, and he has an excellent book. This is really a fantastic work that he's done. Crystal sets to sideband. And you want to get a hold of this book if you want to build anything to do with QRP and interesting homebrew circuits. So what Frank does in this chapter is so good, I just have to go through it. First, let's look at a typical VFO that Frank built, and you can see that he's very similar to the kind of construction that we're all used to. You've got this box, this die-cast box. He's got a big old stable variable capacitor for the VFO. He's got looks like a ceramic form for the main coil. I see all kinds of different capacitors and chokes and trimmers in here. So let's go through some of the principles of VFO design. First of all, low-frequency VFOs drift less than high-frequency VFOs. Well, that shouldn't be too surprising to people, but that's a good principle. If you can build a VFO at a low frequency, generally it will drift less than one built at, say, 20 megahertz or 30 megahertz. So that's a good first principle. Using Jfets. Jfets are ideal for building VFOs. Basically, there's several reasons for this, but Jfets are like tubes, but without all the heating. And because of their high impedances, and because of their PN junction being different than a bipolar, they make superior VFO devices. So we're going to stick with the Jfet. Now, when you're talking about which oscillator to pick, there's all kinds of arguments, and there's some pretty avant-garde style, the Wacker oscillator, and on and on. But I like the way he's thinking here, using a standard Colpitts oscillator. The high C standard Colpitts shown here in this diagram is really a fantastic VFO oscillator. I've built plenty of Hartleys, and I've built clap type oscillators, but I can tell you the best success I've had has always been with the standard Colpitts. What else is he getting into? He's got some other things here. He starts to talk about buffering, proper buffering of the VFO, which is very important. Notice where he's taking the VFO output at the low impedance point of the Jfet, and that's very important. It doesn't matter whether you're building a VFO or you're building a regenerative detector. If you're building a regen with an FET, you want to take your detected audio off the source. Not up here in the drain, not up here where the feedback loop is, or the feedback tickler is. You want to take it off the source. It's the most stable part of the FET circuit. What else has he got? Oh, he talks about low-pass filtering for the VFO. Okay, here we are. This is the good part. 50 secrets of avoiding drift. Wow. First of all, junction field effect transistors. fantastic choice. Seal the VFO in a cast box. So this is going to help in a couple of ways. It's going to help to isolate the VFO from the temperature in the room and wind and things changing in the room, turning on a fan, overhead fan, or the furnace coming on, that kind of thing. All of those can affect the VFO. Also, a cast metal box allows good grounding. It's heavy, and it's going to allow you to get good stability. Use a single-sided PC board. A single-sided PC board, why? Because a two-sided or a three-sided PC board, you can have some capacitive differences depending on how it swells up. As the temperature changes, the board material expands or thickens, and this can change the capacitance across the board, possibly affecting stability. Mount the PC board away from the metal case on standoffs. Get it away from the outside of the case. Choose and mount all the components affecting the LC circuit carefully. Good, solid standoff insulators. You might have heard of using ceramic. Well, the ceramic's not that important, but what's important is that you have a good standoffs and that you're supporting that board in several places, not just one place. Like a diving board tends to vibrate, and that will change frequencies. Now, mechanical stable variable capacitor. Yeah, mechanically stable variable. Nice, solid variable capacitor. This is where you don't want to skimp. This is the most important part. But Mike, I want to use a varactor diode in my VFO. Well, I don't care how good you work with a varactor diode. You've got another error that's going to come in, and he's going to go down here and talk about that a little bit. It's the most stable tuning element, absolutely true. But unfortunately, it's got a couple problems. Problem one, it's nonlinear, so the scale on the frequency tuning knob is not going to be linear like it is with most variable capacitors. Also, you've got a power supply involved. So now you got this DC voltage. This DC voltage could have noise, hum on it. It could be varying by a few millivolts. So a varactor might not be the right idea for a very stable VFO. NPO fixed capacitors are the best to use. That said, we notice that he's using silver dip micas, and I use silver dip micas. I have them, I use them. Are they as good as using an NPO capacitor? No, they're not, because you never know if they're going to be drifting up or down in capacitance with temperature. But that said, sometimes you can find a magic combination of silver dip micas that will work best in your VFO, and your NPOs might work against you because it gives you a perfect capacitor that drifts only according to the coil drifting. And now, even though your capacitors are completely stable, it's your coil that's drifting. So you need to use a capacitor that drifts the opposite direction to overcome that coil. Using multiple NPO capacitors in parallel to achieve a given value. That splits up the current going through the tank, and the temperature of a small capacitor stabilizes quickly, whereas heat builds up more slowly in a multiplate or larger capacitor. So lots of capacitors in parallel are better than one big 820 or 2200 picofarad capacitor. Better to use multiple capacitors in parallel. Temperature compensation for the LC circuit is essential. Now, I've been lucky, maybe you've been lucky, and you've come out with no temperature compensation, a pretty stable VFO. It does happen. But generally, you do need to use temperature compensation in most VFOs. Here we go. Use an air core inductor. Air core inductor, if you can't use an air core inductor, use a ceramic-based core that you wind on. And make sure that if you are using some type of form, that it has good posts on it so that you can tightly wind the wire on the form. You also might have to stake the coil at both ends with some type of epoxy.
to get stability. So powdered iron, variable slug, variable inductors with ferrite and powdered iron cores are a no-no in the VFO. I'm not even in favor of using toroids in VFOs. I stick with either ceramic or air core type coils for VFOs. So he says if you do want to use a core, he likes this one, powdered iron type 7 cores, which are very low permeability. So it's kind of like winding on a rubber tire. You're not getting a lot out of this coil, out of this core. It's more of just a form that you're winding on. So precision voltage regulation for the VFO supply. You might even use 2 regulators. One regulator just for the VFO and one regulator just for the buffer. It's okay to go overboard when you're building a VFO. The VFO should draw as little power as possible. That means if you have a choice to run the oscillator at 3 volts compared to 5 volts, compared to 8 volts, compared to 12 volts, 3 volts will give you the most stability because the VFO will draw less power in general, less heating, more stability. And forget about tube oscillators. Well, I disagree with him here. I've had a lot of fun with tube oscillators, but make sure that if you do use a tube oscillator, that the tube is outside the case and at the top of the case, and make sure that the filament is lit at all times, even when the set is off. The Heathkit Marauder uses this trick. It keeps the oscillator on all the time, the filament lit on the oscillator all the time, and that's an important point. And that is a properly designed tube VFO. Then he gets into using a Vernier dial, very important. I'm using a fairly primitive dial on mine, but still it makes a big difference when you're tuning that VFO to have a Vernier on the front. So then he goes into varactor tuning and how to do varactor tuning and so on. He gives you the advantages on the varactors, and he tells you about the problems with the varactors, and on and on. Anyway, I just wanted to take you through what I thought was a very good synopsis and treatise on VFOs, homebrew FET-based VFOs that Harris has written here, because I didn't want to steal any of his thunder. I think he's done a beautiful job in this book.
So let's take a peek at my VFO. And I actually found the Harris article, the chapter from the book, after I built my VFO. Obviously, I built the VFO back in, it was really the early 90s. Somebody mentioned in the comments that case looked like it was from a test box that he used to use at a connector company he worked for. And I turned the box over and look at this. It definitely was some type of test box. It's got some really cool drill with some, looks like somebody put paint in there. It's got some nice stenciling on it. Yeah, that was a nice test box at one time. So first of all, we're hitting some of the things that were brought up. Definitely. See if I can get this thing to be stable. First of all, it's in a die-cast box. Score. Second of all, the circuit board is stood off from the case, albeit with one standoff. Strike one. Should be more than one standoff for that circuit board. A nice variable capacitor. Okay, that's a win. And to trim the variable capacitor, there's no ferrite slug in here. There's a second little trimmer over here that's used to trim it on frequency. My band switch is this toggle switch, which I just added. That's strike two. You shouldn't be using a toggle switch to switch a VFO, that's for sure. Let's look at the coil. Now the coil is interesting. It's a ceramic form, And it's actually got grooves in it. Look at those grooves. That's groovy. Which keeps the very heavy wire, it looks like number 22, in place. Now this is a 4 megahertz VFO. It tunes just a few kilohertz of 4 megahertz to cover the band that we're interested in, 630 meters. That doesn't look like very many turns. A 4 megahertz VFO with what looks like about 10 or 12 turns. And look at all of those silver mica capacitors that are in parallel. Aha! Maybe we're hitting some other positive things with the VFO. We have the coil with a very nice ceramic form, and we're using capacitors in parallel. So I think that this VFO kind of speaks for itself. It's got some decoupling over here and a regulator. Notice how this regulator is pounded right into the side of the case. It's a little bit close to the coil. That's probably strike 3. We should have put the regulator away from the coil a little bit. Notice the filter feed through. Well, that's a positive. I suppose if we were having a drinking game now, I'd still be ahead with this design, but it's getting close. So there it is, a simple FET VFO. The circuit we can go through, but everything is on this board. Basically, it's a FET and a couple of bipolar transistors as buffers and emitter follower type setup. So that is the VFO that I used in the original 1750 meter receiver, which was tuning from 160 to 190 kilohertz, and now it's been modified to cover the 630 meter band and the 2200 meter band with the toggle switch. And is it stable enough for CW operation? Yes, absolutely. Is it stable enough for whisper? Not really, although I did get some prints, but everything was slanted. Does it need compensation? Probably, but I'm not going to go that far with this. It is what it is. It's working for what it was designed for, which is a CW receiver, and the stability is within reason for what I'm trying to do.
Okay, who am I to argue with W1FB? This is a VFO circuit that he's got in his notebook. And this is essentially what I have in that can. You can see it's an FET type oscillator. Colpitts, this is using a 3819, which is a very nice transistor to use. Or you could use an MPF 102. A lot of people say the 3819 works a little bit better in VFOs. I don't know about that. I do know one thing. It has a different pinout, I think, than the 102. Check that out. Make sure you're using the right pinout for the FET. He's using a couple of 100 picofarad capacitors in the Colpitts. This is a little higher frequency. It's a 40 meter VFO. Down at 4 megahertz where my VFO was running, I used 680 puff capacitors here and more capacitors over here. And I kept the inductor very small. And having that high C, low L style circuit gave me a lot of stability. So I like he's coming right off the source into his buffer. And instead of using this as a source follower, he's coming off the drain and going into a conventional 2N2222 amplifier. And then he's got a little output filter. So this is a VFO that's maybe a little bit more output power than I'm using in my receiver, but it's not far off. So I'm going to call this a good circuit for you to emulate. Notice he's using 6.8 volts on the FET. You want to run the oscillator at a lower voltage. If you can do a better regulator or a separate regulator with the VFO as the buffer, go ahead and do that as well. So this is a good one to follow. I'm not going to promote anything that I could design that would be better than this.